So this is the lecture for the PH 5502 Unit 4 Solid State Physics by Dr. M.R. Gadhvi. Classical free electron theory for the metal. The model was very firstly proposed by P. Drudd. It's a Paul Drudd, some around in 1890. In those days, it was the very first model for a metallic crystal or the metallic property, especially the metal conductors. Because the metal was widely used in the varieties of the technology and the devices and the development of industries. So nobody can predict for any particular metal without any particular model, and therefore Paul Drudd has given the model which was helping a lot in those days. Later on, it comes to the situation that it is not exactly uh, perfectly executing the model, because in those days it was working with the classical theory, and today's we are executing the same model with the concept of the uh, quantum theory. So anyway, as per his theoretical model, the kinetic velocity of the electrons are assumed to have the root mean square velocity, which is defined by C bar, given by the kinetic theory of the gases. And as in general, the gaseous molecules do not interact to each other, and suppose you are visualizing this gas molecule in a container, then they are bouncing to each other, reflecting from the wall with the elastic collision, so not changing the energy and so on. So Paul Drudd has just make a replica of that scenario and that analogy, and therefore he applied the kinetic theory of the gases and their relations and the set of equations on the same free electron of a metal conductor, which are free to roam within the crystallized limit. So for a unit volume of a metal, you can write it out, the momentum P is equal to 1/3 of mn c square, where c is the root mean square velocity of this electron, m is the mass of the electron, and n is the total available number of electrons. So if you consider it's a unit volume of the metal, then number of electrons having a mass m, so that would be the total mass of the system divided by the unit volume, so V will be 1, so ultimately mass per unit volume, so it is replaced by the density. Now it is always better to have the molecular mass, molecular volume, rather than the volumetric volume, and therefore to convert the same relation in a molar volume, it is better to have the same relation as a PVM, where Vm representing the molar volume, and that would be the 1/3 of the mNac square, where m is a mass of a electron and number of electron is replaced by the Avogadro number, and here we are unitizing the uh, uh, molar volume, but at the same time it is considered to be having the 1 kilomole. So nRT, that relation, the standard relation PV is equal to nRT, where n is equal to 1 kilomole, so 1, no need to write it out over here. So 1/3 of m, where n is replaced with the Na, and that is a 1/3 m Na, that is Avogadro number c square, is equal to RUT, and the Ru is a Rydberg gas constant. It is generally represented as the Avogadro number times of the Boltzmann constant, so n into k, where k is the Boltzmann constant. So from this relation we can having a mc square is equal to 3 Ru T upon Na, and therefore ultimately it is are you having also Na, so that Na will be getting cancelled and we having a 3 kt. So ultimately the root mean square velocity is nothing but the 3 kt upon under root of 3 kt upon m, where k is the Boltzmann constant, T is the absolute temperature of a conducting metal, and m is the mass of an electron. So you can ruled out that the root mean square velocity in a conducting metal as per the Paul-Drude classical theory or the classical model for the electron gas theory, that is given as the root mean square velocity of a free electron gas is inversely proportional to the square root of its mass and directly proportional to the square root of the absolute temperature of the chosen conductor. So if I will calculate, let us say for a metal, for any conducting metal like copper at a 20 centigrade, then if I will replace T as a 20 centigrade and mass of an electron, then it would be C. Here the limitation is that irrespective of the material, the C is remain almost constant. Well, in that case, it is not always true, because electrons is moving within the cage of a lattice structure. So the scenario which is offered by the copper is not true for the aluminum, and that's why the velocity of a free electron in each lattice may differ, whereas in this system they are considering the identical. So from this particular root mean square velocity, one can also find it out the relaxation time, and therefore the tau is equal to lambda by root mean square velocity or the kinetic velocity of the electron or the free electron, and therefore the lambda into inverse of 1 over c, or the inverse of c, that is under root of m upon 3 kt. So this is nothing but the relation of this one, relation of the root mean square velocity is replaced by the equation, and therefore lambda into c is nothing but the time, and this is relaxation time. So now for any particular conducting material, if one has to do a vital test for the validity of the theory, then the very fundamental one is just measure the electrical conductivity of that particular conductor using the Ohm's law. So if you are executing the Ohm's law, then we can write it out the current density as a function of current and the cross-sectional area. So J is basically I by A, where I is the current passing through the conductor through the cross-sectional area in a unit time, when the applied potential to the conductor is given. So that is E is given by the minus dV by dx. The minus sign is indicating that the flow of electrons is, or the velocity of the electron under the guidance of the electric field is in the opposite direction to the direction of the applied field E, and therefore the minus sign is indicating over here. So anyway, so for this particular I, the current of this conductor, I can write it out A into J. So this is A into J, and the fundamental law of the Ohm's law, I can write it out I is equal to V upon R, and therefore the current is, I can also write it out from the above relation, that I is equal to 1 over J is equal to AR upon V. Now this voltage is across the length of the conductor. So if I consider the length of the conductor is L, then this V I can put it in terms as a EL. Okay, and this A, that's the cross sectional area, is as it is, and R is a resistance, so it's in fundamentally R is proportional to L by A, and if I will remove the proportionality constant, I should have the resistivity. So R is replaced by rho, that is the resistivity, into L upon A, into L upon A, and that way the A will get cancelled, L will get cancelled, and the rest part will be the rho upon E. So ultimately I is also explained by rho upon E, that is the resistivity upon applied potential. So now in nutshell, the conduct for a conducting material, the current density can be written as E upon rho, E upon rho, that is the, because it is 1 over J, so if I take the inverse of that, that is the applied field upon resistivity of the chosen conducting material, and 1 over resistivity, that is nothing but the conductivity, and therefore J is equal to sigma E. So this how we can also having the relation of a conductivity or the current density with it, conducting material current density. And in principle, if you are looking how exactly happening within the conducting material, so let us now try to underline how the velocity of the electron within a conducting material is taking off. To see this particular relation, to derive this particular relation, one can do the following calculation. What we are planning to do, let us assume that we are applying a field that is in the x direction, so I am considering the E suffix x, so the subscript showing the direction of the applied field, so that is in the x direction, and therefore all the electrons are accelerated in the direction of the x. And let us underline one of the electrons, let us say it is a ith number electron, so I am using as a acceleration of the ith electron in the direction of x. Okay, so with the fundamental of the Newtonian equation, I can say that F is equal to m into acceleration. So now force is also represented in terms of, for my present case, so that would be Ex, so that is my applied field E, and chosen charge Q, that is a minus E, that is the electron, so minus Ex, that would be representation of the force, and m into a, so mass into acceleration, where I can again be specified that acceleration into the direction of x. So ultimately for the ith electron acceleration, I can write aix. Okay, and aix, and this m I am taking down here, so it would be a minus e, small e, that is electron, capital Ex, that is the applied potential, divided by the m. So acceleration can be rewritten as a change of velocity. So derivative of the velocity Vix. So as I wrote here the subscript value Ix, that is the ith electron into the x direction, the velocity of the ith electron into the x. So d by dt of V suffix Ix. So RHS will be still remain as it is. Here I am putting a subscription value, that is a Ex, that means this is under the observation of the potential, that is Ex, or the applied field Ex. So the acceleration is occurred due to the applied potential. But as we are knowing, in a conduction material there are plenty numbers of electrons, so ideally a velocity should be the average velocity. Now exactly how I can visualize the average velocity, so it is written very nicely here. The average velocity is nothing but a summation of all the ith electrons in x directions are moving under the influence of the applied electric field, that is Ex, and I value I am running from 1 to n. because my total number of electrons are n, then naturally I am running the ith value is right from 1 to n, and this would be the Vix. So I am taking the summation of it, and since there is a n number of candidates are there, so I am divided by n, so that would be my average velocity. Okay, so now the current density I can rewrite in the terms of, rather than the individual velocity of an ith electron, I will be using n number of electron multiply by the average velocity in a x direction multiply by the charge carrier. So that would be and charge carrier is electron, so it's a minus e, so ultimately it's a minus nevx. So jx, so the current density into the x direction can be written as minus nevx. Let us say it's equation number 6.5. So let us again go with the relation number 6.4. Then my LHS is still d by dt average, or the derivation of the average velocity in the x direction can be written with the idea of from the equation of 6.5, then it is a Vx is nothing but the jx upon ne. So jx upon ne, and we should take a derivative of this one, because on LHS it's a derivative of the average velocity, so it is a derivative of j current density derivative with respect to time. So basically this relations we are able to deduce from the equation 6.5. So now let's move ahead with this. Then my LHS component I can equate with, so my equation 6.6 and equation 6.4 I can equate, because my LHS of 6.4, my LHS of the 6.6 are equal, so I am comparing both RHS of this 6.4 and 6.6, and therefore it becomes 1 upon any derivative of the current density, so d by dt of j of x is equal to e by m ex, when negative sign of on either side will be cancelled out. So ultimately the derivative of current density is equal to certain constant into ex. This ne will go here, so it becomes n e square upon m, where n is a number of like free electron in a conducting material, that is constant. The charge of electron is also constant, and mass of electron is a constant, so I wrote here the constant over here. Now 6.7 equation is indicating very nice information. You can see that there is a constant ex, that is a so far the constant ex. This free electron model leads to a current which is increases linearly, with the time, and I think such kind of the reveal is never possible through the Ohm's law. But anyway, this is a just identical development of a model using the Ohm's law. So by chance in exam someone asks you to prove that whether the Ohm's law is not proven by the classical theory of electron gas theory, then you can go with till the point